I'm Dr. T, and welcome to my office. Today I'd like to talk a bit about waves. Waves are an interesting thing, they're not really a thing per se. Don't get me wrong, they totally exist. It's just that they're not an object. A wave is energy traveling. It is not a substance. So it's as energy travels through a thing, you get yourself a wave. Now, with when I'm talking about waves, there is a little bit of an asterisk in that light is sort of a wave. It is a wave, and it's also a particle, and it's really weird, so I will cover that in another video. But what I am talking about does mostly apply to light, as well as things like sound, ocean waves, and any of your other waves. Even, the wave, Although that's a little bit different than the others. Okay, so waves come in two predominant styles. You've got the transverse wave, which is your classic ocean wave, and your longitudinal wave. This is what sound's going to be. So instead of doing up and down, it's going to go back and forth. And when you're looking at these, the medium that's going through doesn't actually move. So if you're looking at an ocean wave, the water isn't moving, at least not back and forth. It's going up and down. And if you're looking at sound, whether it's going through water or air or through a solid substance, it doesn't travel. The particles of that substance don't travel. They move back and forth a bit, but that's all they do. They don't go any long distance traveling. So that makes waves rather interesting. It also means that, once again, with this somewhat weird exception of light, waves have to travel through a medium. They have to go through something. That's why there's no sound in space. There's nothing for sound to travel through. Now, when we look at waves, there's really kind of four key properties of waves that we can look at. So let's imagine some ocean waves. These are, the easiest ones to imagine. So, you got the ocean. Or really, if you're a buoy in the ocean, it would just be up and down. Because remember, the particles of the ocean don't really move over that much. Once the wave hits the shore, a couple of weird things happen in that case. But if you're out in the middle of the ocean, you're just kind of going up and down, maybe in a little bit of a circle, but you're not traveling with the wave. The wave is going through the ocean, not moving the ocean. So the first property is, how far up and down do you go? Is it a wave or is it a wave? So in this case, what we have got is amplitude. Amplitude is simply the height of the wave. How powerful is this? And typically for most waves, asterisk except light, this is going to be describing how much energy is in the wave. So the greater the amplitude, the more powerful that wave is, the more energy that's in that, the more energy that's traveling along. The next property is the frequency, and that is how often a point is going up and down. So if it's like, that's one frequency. If it's a, that's a different frequency. This is given the Greek letter nu. It looks like a squiggly V, but it is the Greek letter nu. And this is usually given units of hertz. Hertz are 1/seconds. Obviously, you might do things like kilohertz or megahertz, multiples of those to compensate for how fast things are going. The next property is wavelength, and so if you think of a wave, it's traveling, it's going if you're kind of following the wave. You've got two crests or two troughs, or any two spots. You can measure how far apart those are, and that is going to be your wavelength. So if you imagine you're in the ocean, you can see the tops of the waves. Well, how far apart are those tops? If you combine, so if you multiply the wavelength and the frequency, what you'll get is the speed of the wave. How fast is that energy traveling through the medium? And that speed is usually going to be controlled by the medium itself. That's why you get different sounds when you're above water versus underwater. You need a special microphone for working underwater because the speed of sound changes depending on which medium you are. If you're playing a stringed instrument, that's why twisting the strings, making them tighter, changes the speed of the waves, and that's going to change the type of sound that comes out of those strings. And then the last part is speed. So that's the last variable. Now, sometimes you'll see an equation where lambda nu equals c. That lowercase c, that's going to be the speed of light in a vacuum, which I will, once again, more on that when we cover light. But that guy is going to be a fixed speed, but that is specifically light in a vacuum. If you run light through other stuff, due to the weird magnetic properties of the electrons and the photons that make up light, it gets all bizarre quantum physics-y here. The light actually slows down as it goes through those, so its speed does vary as well. Which is useful, because that's how glasses work. And, you know, I need those. Those are helpful. Okay, so with that said, have a wonderful day.